Swayam Prabha. Digital India. Educated India.
Okay, so let's first do the MLE, maximum likelihood estimation, right? So MLE, as we have seen in the previous lecture, it's nothing but taking the log likelihood and maximizing it, right? We can also think of this as taking the negative of the log likelihood and minimizing it, okay? Both are equivalent. So maximum likelihood is equivalent to minimizing the negative of the log likelihood. I'm working with the negative because it will help us draw parallels with the least square objective that you have seen before. Because we will be doing a minimization rather than maximization. Because we have a loss function, we want to minimize rather than maximize, okay? So the negative log likelihood will be negative of log of P of y given capital X comma W, which we have already worked out in one of the previous slides. So it will be minus log of this product of this whole thing. Okay, so this is our likelihood that we already saw. This log of this product will turn into a summation, right? And the negative log likelihood will turn out to be this quantity. Okay. Log of this product. So again, note that the first term, this beta by 2 pi will not matter because it doesn't depend on W. So we can just ignore it. This is just a constant as far as the minimization with respect to W goes. So the negative log likelihood will be just this expression, right? This is a function of W. Beta is a constant, right? So in fact, we have this beta by 2 in the front. We can even ignore this. We can just we can forget about it and we can just have this term and that will be equivalent, right? So we have seen that if we start with a probabilistic linear regression model and if we do maximum likelihood estimation, we get an objective function which is nothing but the squared sum of squared losses, right? Which is exactly the same as the original objective that we have seen before, right? So this shows that there's a connection, right? So even thinking about the problem probabilistically, is equivalent to using a loss function, okay? But of course, there are other benefits that we will look at shortly. So if we solve this objective function, we will have the same solution because the solution will not be any different. It will again have WMLE. So WMLE will be X transpose X inverse X transpose Y. The exact same solution that we had for the unregularized loss function version of linear regression. Okay, any questions on this, up to this? So far we have only established the notation. We have talked about the likelihood model, the prior distribution, and we have shown that doing maximum likelihood is equivalent to solving this least square minimization problem, which gives us the same solution that we get by solving least square. How about doing a map estimation now? Okay, note that map estimation will also incorporate the prior distribution. Okay, so if you recall, map estimation is nothing but the MLE objective plus log of the prior. Okay, so log of the prior will be, so we'll work with the negative log of the prior. So minus log P of W given lambda will be this quantity, right? So it will turn out to be just lambda by 2 times W transpose W. Okay, minus log this product. Okay, so this is what we will get. So again, if you recall, the only difference between MLE and map was that in MLE, we only had the log likelihood being maximized. In map, we have the log likelihood plus log prior. If you recall the Gaussian mean estimation, we had the log likelihood plus log prior also. Note that I have a negative because I'm solving a minimization problem. Okay, but other than that, we have the negative log likelihood and the negative log prior, and we are doing a minimization. Right? So the W map will be the solution to this problem. We already saw that the negative log likelihood is this term in the beginning, and the negative log prior is this term that we have from the above. Okay, so the W map will be argmin, which is the minimization with respect to W of this combined objective. Note that this objective has 2 parts. One is the sum of squared errors. The second is basically the sum of the coefficients squared. Okay, so this is the W map. Okay, so what will be the solution to this problem? Well, it's actually not all that hard. You can, by the way, you can also rewrite the same thing in this form. So you can multiply both terms by beta because beta is constant. So I can multiply the first term, well, not beta, but actually beta by 2 by beta, right? You can multiply, so you can multiply both terms by 2 by beta. So this beta by 2 will go away, and then you'll have a lambda by beta here. So I'm just scaling these 2 terms. Because these are constant, so I can safely do this. So what is the final objective? for the map estimation problem, it's argmin of basically this squared error, sum of squared errors, plus lambda by beta times W transpose W. Okay, so this is our map objective. Again, this is not very surprising. This is not very different from L2 regularized version, right? So L2 regularized version was exactly the same. There we had a single constant, like tau, which we denoted by tau. But here we actually have this tau thing defined in terms of this lambda by beta, where lambda and beta are the hyperparameters of the likelihood and the prior distribution. Okay. So in the L2 regularized thing, we had just had a single constant here. But here we are saying that in the probabilistic version also we have a constant, but it's in terms of two other constants, lambda and beta. It's lambda divided by beta. Okay. Also note that we are assuming that lambda and beta are known. However, we can estimate these parameters as well. Okay. Okay. Any questions on this before we move on? So again, we have, yes. It's not about the use. So the thing is, whenever we solve, okay, so the reason why we are working with a negative log likelihood rather than log likelihood is because we are solving a minimization problem. So I can also work with maximization problem, in which case we'll just work with the log likelihood. But here, rather than solving, because typically we think of loss functions, you know, we minimize loss functions. I wanted to express this problem as a loss function rather than likelihood, which is why I'm working with negatives of everything. Yeah. Yes. They don't have the same variance, right? The prior distribution has the variance defined by lambda. The likelihood has a variance defined by beta, right? So beta is like the noise variance in the data, in the y's, right? So there are two types of variances here. One is the variance in the likelihood distribution controlled by beta. One is the variance in the prior distribution over, right? And there's a rule of both these, you know. So if you expect that the data is very noisy, then typically beta will be large. Well, small. It depends on, you know, precision, right? So if the noise is large, then beta will be small, right? Likewise, if you expect, if you want to regularize more, right? If you expect W to be close to 0, very strongly, if you believe that, then you would set lambda to very large, okay? But as I also mentioned earlier, you can actually learn the right lambda and right beta from data, which is not what we are talking about today, but you can do. I'll show you how you would do that. But these things can be learned from data. Okay, so anyway, just to summarize what we have done so far, we have looked at both MLE and showed that it's an unregularized loss function minimization. We have looked at MAP and we have shown that it is equivalent to a regularized loss function minimization, where the regularization is in terms of the L2 regularizer, W transpose W. Where the regularization constant that you have in the regularized version, tau, is nothing but lambda divided by beta. And not surprisingly, the solution will be x transpose x plus lambda by beta times I inverse x transpose y. In the previous case, we just had tau times I, right? So the solutions are not going to be any different in this case also. Clear? Yeah. So we have seen both MLE and MAP. And again, you can think of this, MLE and MAP using this illustration. Think about this using this illustration, which is similar to an illustration that I showed in the previous class as well. So if you think of so in this case, the red curve kind of, it shows the likelihood model. Okay. So this is the probability of y given x comma w. Okay. Likewise, this green curve is p of w. Right? And this blue curve is p of w given the posterior distribution of w given the data y and x, right? And the map is nothing but the maxima of the posterior distribution, right? Whereas WMLE is the maxima of the likelihood distribution. And again, as you can see, the prior's mean is somewhere here, right? And the MLE is here. And the map is kind of a compromise between the MLE solution and the prior's mean. So, so in some sense, when we do map estimation, the role of the prior is to shrink the weight vector or move the weight vector from the MLU solution toward the prior solution, toward the prior. Okay, so it will be kind of a combination, a weighted combination of the prior's mean, which is 0 in our assumption, right? And the maximum likelihood solution. So again, just to summarize the MLE and MAP for linear regression. So we saw that the solutions for the MLE is equal to x transpose x inverse x transpose y. MAP solution is x transpose x plus lambda by beta times I inverse x transpose y. Okay. So I did not do the full derivation of how you get this, but I believe you would have done it in the linear regression lecture. This is just like taking derivative with respect to W, setting it to 0, and you get this solution. Okay. Yeah, so what is the difference between these two solutions, MLE versus MAP? Just as a recap, MLE does not do any regularization. It does not use any prior, which is why it does not do any regularization. And essentially, the role of the prior is to regularize the solution. So one other message that you can, as a takeaway message you can think of, is that whenever we use a prior in a model, it in a way regularizes the model parameters. Okay? So it's a probabilistic way of doing a regularization in the model. Okay, so that is what prior does. So prior, well, you can think of it as injecting the prior knowledge into the problem, but also in terms of regularizing the parameters. Okay. Okay, and map here is using a Gaussian prior, so map which acts as a regularizer on the weight vector. Now, as you can see here, so what is lambda? Lambda was the precision of the Gaussian prior. Okay, so if lambda goes to 0, then this map solution approaches the MLE solution. So if I set lambda to very small or maybe exactly 0, then these two solutions become become identical, right? Which means that as the prior's precision goes to 0, right, which means that the variance is like very large, right? There is no like, okay, so let me again use the picture to show the idea. So if you have, so a Gaussian, as I said, it looks something like this, right? So if the precision becomes very, very small, then it means that the variance has become very, very large, right? So it means that the Gaussian will become something like this, like a very flat distribution, right? So what this flat distribution means that there is no preference that we are assigning to any specific value of W. So there is no prior information we have about that. We expect that every value of W is equally likely, okay? Which means that we are effectively doing maximum likelihood without any regularization in the model. Okay? So which is why you can see that if lambda goes to 0, map solution becomes equivalent to MLE solution. Okay. So now learning the weight vector is not our final goal, right? So we want to learn the weight vectors, and then we wish to make predictions, right? We get some future test data. Let's say we get a new input x star, and we wish to predict what y star will be. Okay, so that is what we wish to do, right? How do we make the prediction? Well, we now have a probabilistic model. So rather than just predicting what y star is, we can now actually predict the mean of y star, okay, along with the variance. Okay, so how much uncertainty we have about the prediction. Okay, so how do we predict y star? Well, we just apply our likelihood model, right? We say that what is the distribution of y star? Again Gaussian, because this is what our definition was, right? We said that P of y given x is Gaussian. So if we want to compute P of y star given x star, it's going to be a Gaussian with mean being, if we are using MLE, then it will be W MLE transpose x star. If we are using map, then it will be W map transpose x star. So whichever solution we have, we'll just do the transpose of that times x star. So that becomes our mean, the mean of the prediction, okay? But there's also a variance in the prediction, okay? And what is this variance? Just beta inverse, okay? Now this is not very interesting. So if we say that every prediction will have a mean, so mean is definite. So for every input x star, we will have a different mean, W transpose x star. But the variance is just beta inverse, right? It's saying that for every future test point, I will have the same certainty or uncertainty, right? Just beta inverse. So this is, I will remove this restriction when we take the fully Bayesian approach. So the thing is, this is kind of a limitation of the MLE map approach. First limitation is that MLE map only give us a single estimate. Okay, they don't give a distribution. Okay, we only get either this solution or this solution, right? We can use this solution to predict the mean of a new data point, of the output of a new data point, but we don't really get any information in the variance part because it simply says that the variance is just beta inverse. It's the same variance. No matter which x star I take, I'll get the same beta inverse. Okay, so it's not of much use, right? So I mean, so it's good in the sense that, well, the model is good in the sense that we are getting a different prediction, the mean, but this part is not very nice because it's just saying that constant variance. Every point, no matter how far from the training data it is, it will have the same variance, right? We will remove that. We'll solve this issue shortly when we take the full Bayesian, posterior averaging. So So note that if we are using MLE or map estimation, then of course so you can think of this as the predictive distribution, right? So this is the predictive distribution of the output given the input. Okay, both of these are predictive distributions, right? Both these predictive distributions have different means for different inputs, but the same predictive variance for different inputs, which is something that we don't like, and we would like to solve that issue later on. Okay, so we have done MLE map. Both are point estimates, right? They both allow us to get the predictive distribution in this way. Again, note that if we only want y star, there is no single y star. We can only talk in terms of the mean of the y star, which is given by this quantity or this quantity, right? But we also have the variance, which we can compute in a more rigorous way, rather than just saying that the variance is the same. Now, we would like to go beyond the point estimate, right? We would like to get the full distribution over W, rather than just saying that it's a single MLE or map estimate. How do we do that? Well, let's do the full Bayesian inference, where we'll infer the full posterior distribution. So we will infer the distribution P of W given X comma Y. How do we do that? Well, first of all, the notion of conjugate priors or conjugacy helps here, because the Gaussian prior is conjugate to Gaussian likelihood. So I talked about this aspect in the previous lecture as well. So, so long as the prior and likelihood both are Gaussian, we can actually get a closed form Gaussian posterior. Okay? So the posterior distribution over the unknown, which is weight vector, can be defined like this. So again, this is W given everything, the data. Okay? So you can even ignore beta, and so I've just written beta, lambda, everything, just to show all the hyperparameters. But essentially, this is Bayes rule. W given a bunch of stuff is basically, or W given the data is data given W times P of W divided by P of data. Okay? So this is a Bayes rule. Okay? Using this Bayes rule, we can compute the posterior distribution over this left-hand side. We already know that the first term, this is the likelihood distribution, this is Gaussian. The second term is also Gaussian. Okay? So when we multiply these two terms, we actually get a Gaussian posterior distribution. And this is an exercise that I have the full derivation. So I'll just walk you through the derivation so that you hopefully don't feel lost. But it's actually just mechanical, walking through a few steps. So I will show you the algebra in the next couple of slides. But the basic, the final expression that you will get for this posterior will be a Gaussian. Again, due to conjugacy, Gaussian likelihood, Gaussian prior, we will get a Gaussian posterior distribution, which will have a mean that I'm denoting by mu and a covariance matrix that I'm denoting by sigma, where the mu and sigma will have the expressions given by these. Okay? So sigma will be this quantity in blue, mu will be this quantity. Okay? So the posterior distribution over W that we will learn for this model will be a Gaussian with mean mu and covariance matrix sigma, where sigma is given by beta times x transpose x plus lambda I inverse. And mu is basically x transpose x plus lambda by beta ID times ID inverse x transpose y. How we are getting this expression, I'll show you shortly. But there are standard rules. There are results that you can directly feed in the expressions, and you can get these results. So I'm not showing you those results right now, but I'll show you the derivation actually, so you know how to do this for a general case. But the basic idea, basic message is that the posterior distribution has a closed form. It has a mean. Okay, so the posterior distribution over W has a mean vector. So this is a mean vector of D dimension, and this is a D by D covariance matrix. Okay, so we have the full distribution now. So let's go over the derivation. Okay, and the derivation is basically based on the completing the squares trick, which we also tried in the previous lecture. Okay, so the idea is that we are trying to find this distribution over W, right? And we kind of know that it's going to be a Gaussian distribution. Okay, so this distribution must have the following form. Okay, so if it is a Gaussian, then it must be in the form exp of minus W minus something transpose. Well, I think I'll have to. Okay, so let me just write it here itself. So the basic idea is that if I'm trying to compute the posterior distribution over W given everything else, it has to be it will be a Gaussian, and the form will be basically proportional to exp of minus W minus mu transpose sigma inverse minus half as well, and then W minus mu. So if I can multiply things together and try to represent it in this form, okay, where I have the final expression as W minus something transpose sigma inverse W minus that same thing, then I can identify mu as the mean of the distribution and sigma as the covariance of the distribution. And in order to get here, I have to like massage my expression into a quadratic form, okay, and that is what I'll do in the next couple of slides. It's actually not like a very complicated derivation, but I'll just show you the brief idea. Okay, so we'll see that when we multiply this likelihood and this prior, we actually get this posterior distribution. Okay, so this is the posterior distribution. It's proportional to the prior times likelihood. I'm ignoring the denominator of the Bayes rule, okay, because it will not matter in this case. We will, even without computing the denominator, we can identify that this is a certain Gaussian distribution with a mean and a variance, with a covariance matrix. So the first term is this Gaussian prior. The second term is the likelihood, Gaussian likelihood. Okay. Once we plug in, the first term is this green. This is the prior distribution. The blue term will look something like this. This is the likelihood term, right? All we have to do now is basically multiply these two things, arrange the terms in a certain way, and then try to identify this as exp of minus W minus something transpose sigma inverse W minus something. That is all we will do. So we'll just like multiply these things and we'll just arrange terms in a certain way. So now, as it turns out, you won't readily get that squared form. So you'll get something like W transpose something times. So once you multiply, so all you have to do is basically multiply things, and then you simplify further, and you get this expression. It looks something like minus half times W transpose this term times W minus some constant times W transpose another thing. Okay, so this is not yet a squared, so I can't write it as W minus something squared, because W minus something squared is W squared plus that thing squared minus 2 times W times that thing. So we don't have the constant, the third thing, right? But the third thing can be, it's something related to X transpose Y, which is a constant, right? So I can just add and subtract, and then I'll complete the square, which is why I'm calling it the completing the square trick. So it's just like a bunch of algebra. So the slides will be available, so you can just go over the derivation once more. So I can do the square, completing the square trick, but by now you might already have started seeing some of the terms that we had in the covariance matrices, right? Covariance matrix and the mean. So if we complete this square, do the completing the square trick, we will eventually find that this actually has the form of a... So the basic idea is that a Gaussian distribution is quadratic in the variable, right, over which it is defined, right? So it has a quadratic term and it has a linear term. So whenever you try to find the posterior distribution, you have to identify that there is some term where you have W transpose something times W, and then another term where you only have a W transpose something, right? And those terms can be used to basically identify what the mean and covariance matrix is, right? So you just compare the form, Gaussian form, and then you'll immediately see that the covariance matrix turns out to be this, and the mean turns out to be this quantity. So again, as I said, the derivation is not super important. The idea is important that, and you can just rely on the fact that the prior was Gaussian, the likelihood was Gaussian, so the posterior would be Gaussian due to conjugacy. And you don't even have to do these derivations. If you are like going to use these kind of things in later on, you can just like use the standard, you can just look up the expression and you can just plug in, and so you don't have to derive these things by hand. All right? So, okay, so so let's summarize what the posterior distribution is. So P of W given the data and the hyperparameters is a Gaussian with mean mu and covariance matrix sigma. Sigma is given by this expression. Mu is given by this expression. Okay, so what additional information we have in this case about W? In MLE and MAP? Yes, right. So when we did MLE or MAP, we only got a point estimate, right? So we got X transpose X inverse X transpose Y, or at best X transpose X plus lambda by beta times I inverse X transpose Y. So in the MAP estimate case, the MAP estimate was exactly this quantity, if you recall, right? But in this case, we are actually getting a full distribution with a mean that has a mean, which incidentally happens to be the MAP estimate, because for the Gaussian, the mean and mode are the same, right? I made this point in the previous lecture also, because when we were doing the Gaussian posterior distribution, the mean of the posterior is the same as the MAP estimate. Because for a Gaussian, it's a symmetric distribution, so the mode is the same as the mean, okay? So the mean is this, the covariance matrix is this. The additional information that we have here about W is the full covariance matrix. So we not only learn a single value, but we learn the full distribution over W. Okay, so this covariance matrix tells us about how what is the certainty or uncertainty about the weight vector W. Okay. So as I mentioned, mu is the mean of the posterior, which is the same as the map estimate of W. Also, if you notice, if I simply set lambda equal to 0, then we actually, mu simply becomes the MLE solution. Lambda equal to 0 means basically we don't have any prior. We have uninformative prior. Keep in mind that the main difference is that whereas in MLE or map we only had a point estimate, here we are getting a full distribution over W, okay, which we can use to make predictions now, okay. Okay, because so that is the case when so now in the previous case when we had MLE or map, we could only use the single estimate to make the prediction, right? But now we have a full distribution. So so how do I use? There is no single W, right? So how do I use this entire distribution to make prediction? So if I get a new X star, how do I predict Y star? Okay. Exactly, the idea of averaging. You can of course say that, well, I'll just use the mean. That's a quick approximation, right? Or the mode of the distribution. But in order to be more rigorous and in order to take into account the uncertainty about the weight vector, you would ideally want to average over all possibilities of W, as we did in the previous lecture as well, right? So that is what we will do next.